Good afternoon, and welcome to Smithsonian Gardens webinar series, Let's Talk Gardens. You can see my garden behind me is really healthy today. And it's really healthy because I have made sure that I have matched the plants with the correct soil type. And we're going to talk about soils today and a project that we have been working with soil consultants that is helping Smithsonian Gardens have the best type of soil to be able to protect our collections that are in the gardens. But welcome. My name is Cindy Brown. I am the Education and Collections Manager at Smithsonian Gardens. And I welcome you to put your questions in the chat box today. Without further ado, I want to introduce you to Marisa Scalera. She's one of our landscape architects and has been working with our soil consultants on this very special project. Marisa, would you tell us more about this project and how we got involved in it? I'm going to disappear. Oh, I'm sorry. I apologize. I'm going to disappear and let the three of you take over, and I'll see you at the end to be able to come back and answer questions.
Thank you, Cindy. And good afternoon, all. I am Marisa Scalera. I'm a landscape architect with Smithsonian Gardens. I am pleased to introduce you all today to my two colleagues, Paul Josie, principal with Wolf Josie Landscape Architects, and Ted Hartzik, senior scientist with Olson. Together, we are very excited to reveal our brand new hot off the presses Smithsonian Gardens Soils Management Plan. Before Paul and Ted get into the details, our team wanted to provide some background for this well-needed Smithsonian Gardens project. This is a project that we completed through the Smithsonian's Collections Care Initiative to support stewardship and care for one of our Smithsonian's living collections, our Smithsonian Gardens tree collection. Many of you are aware that Smithsonian Gardens is a public garden and an accredited museum. I see many of our colleagues from public gardens around the region in the audience today. Welcome all. And so most of you are also aware that the trees on the Smithsonian Gardens campus are accessioned collection items. A useful tool for us at Smithsonian Gardens when discussing trees and soils with our colleagues here at the Smithsonian Institution has been to utilize the language of collections. A critical concern for collection managers throughout the Smithsonian Institution is the appropriateness of the materials used to house museum objects and collection items. So too, a living horticultural collection requires appropriate housing, in this case, healthy soils, to provide the substrate for tree roots, essential macro and micronutrients, and necessary moisture. As you all in this audience are aware, soils form the literal foundation for our landscapes and our gardens. They are arguably the most critical component in the success of our gardens. And that said, this housing for our collection items is also vulnerable to a wide variety of impacts, including heavy visitorship. Our gardens see 25 million visitors each year. But that also comes soil compaction. We also see an abundance of landscape construction projects with their accompanying staging and access issues, varying soil specifications, which we'll get into in more detail later in this presentation. Let's move to the next slide. The Smithsonian Institution currently has a number of sizable capital design and construction projects in progress. Many of these impact Smithsonian Gardens gardens, landscapes, and living collection items, as well as the soils that house and support them. Given the process for capital design and construction projects, we've had numerous soil consultants working as part of varying consulting design teams on projects across our campus. With each new project, each new national design firm, each new soils consultant, Smithsonian Gardens has encountered a dramatically different approach to soils design and soil specifications. These approaches have not all proved successful on our campus using metrics you'll see presented later in today's presentation. And so we at Smithsonian Gardens perceived a need to develop our own consistent, resilient, regionally appropriate, campus-wide approach to soils design and implementation that that we can proactively share with outside design teams at the outset of a design project, rather than passively reacting to these varied approaches to soils design. We also perceived a need to assess our existing soils and to consider soils remediation projects where needed on our campus. You can go to the next slide, Paul. So to that end, Smithsonian Gardens proposed and received funding for this project that you'll see presented today. Our study boundaries are highlighted with a red dashed line on the slide you see before you. These are the Smithsonian's gardens in DC's monumental core adjacent to the National Mall, and also our gardens at the Donald W. Reynolds Center for American Art and Portraiture. The intent is for this document to serve as a guide for future design and construction projects, and also to serve as a tool for Smithsonian Gardens to analyze and remediate our existing soils. The result is a comprehensive soils approach that we look forward to sharing with you all today. And with that, I'll hand it over to my colleagues, Paul Josie and Ted Hartzick, to dive into the details.
All right, thank you, Marisa. Well, we'll start off with just introducing our team. We had a terrific group. We had a lot of fun putting this together. From Wolf Josie, myself, Mary Wolf, and Dustin Smith, and then from Olson, we have Ted Hartzick working on all the soil details, and then Marisa and Jake Hendy, the arborist, Marisa, the landscape architect at Smithsonian Gardens, have been intrinsic and throughout this process really involved as a narrative back and forth, and us all sort of realizing these new details about the site and sort of a path forward. So, as well as countless horticulturalists and other people we've interviewed and talked to. So it was a big process, but you know, and really a lot of fun. So. A little background about us, our work, we work on a lot of different landscapes. At Wolf Josie, we have working on the District Wharf currently, so very urban sites, mostly, you know, this is a large waterfront project in Washington, D.C. That is about a mile of continuous waterfront and about, you know, 20 some acres of new development, but also working on UNESCO World Heritage sites such as the Lawn at University of Virginia, looking at studying their trees and how a succession plan for the future for those is, and then doing soil consulting also in areas in Miami or other projects, working with the Smithsonian and the Botanic Garden. So that's our background as landscape architects. Ted, as a soil consultant, has worked, he's based out of Kansas, Overland Park, Kansas, and has worked Seattle to Washington. He's working on currently on the Air and Space Museum in Washington, D.C., but lots of very notable, exceptional projects, Houston, St. Louis. And so we're really excited to work together with Ted on this. So we'll start off with a little bit of history of the area. And this picture is so striking. It's you can imagine at one time the shores of the Potomac really rose right up to the base of the Washington Monument, and it almost is like this lighthouse on the shore. That's a very different picture than what you see today. And so the hydrology of this site really was quite important when we started to look at how water used to move through this site. This is looking at around 1818. You can see a notable Tiber Creek watershed moving through the site, and then again that Washington Monument right on the shores of the Potomac there, and over time, you know, 1818, looking at 1862, the creation of the city canal, and this was a very channelizing the Tiber, and then, you know, starting to actually start adding fill, more of a hard edge, and then even further. You see now today's water line, a lot of fill moving into these areas. And then the channel has been, the canal was closed, the Tiber Creek completely piped. Now you have the Tiber sewer routed to the Anacostia River and a number of other, you know, large sewers underground directing water. So it's a very different environment than it was. And even looking at it from a section standpoint, the topography, this is overlaid on a 1791 map of the Tiber Creek. And this is where you can see the National Museum of the American Indian right you know, on the shore or the banks of the Tiber Creek. But then the fill line is that pink where soil has been brought in and imported over time to add soil into these areas. So also, looking at, the National Museum, but how these transition with National Museum of Natural History. Sorry, this is the Smithsonian Institute building being the only one that really is on terra firma, truly the grades. Others have been sort of cut and filled over time. But as you get down into National Museum of African American Art and Culture, you can see a considerable amount of fill has occurred in that area over time. And there's likely groundwater still moving through there, and there's instances of sort of groundwater intrusion and saltwater intrusion into that foundation still to this day that they're seeing at that site, which makes sense given the huge amount of fill that has been brought into these sites. And that fill is soil brought in from other areas. So looking at it from a different perspective, from a timeline of construction, starting in 1855 with the Smithsonian Institute building, you can slowly see this gradual construction of what we know today as our Smithsonian Gardens, going through 2016. But it's a steady development. It's happening every 30 years or so that we see change happening. And with that change is a different approach to soils. And so what we saw was in the 1800s, we were seeing a lot of, well, this is again, terra firma, the native soils of the area. So these two buildings were native soils, but then there's imported fill happening pretty much until the 1960s, where soil was just brought in wherever it was available. There was no significant consideration for where that soil came from. Some of these were, well, anyway, some eventually came in from dredging and stuff, but a lot of development in the area would bring in additional soil as needed. But the 70s really changed things with soils, where engineered soils, where you're mixing sand, soil, compost in various degrees, and to create an engineered soil. This allowed soils that was also kind of a byproduct of different industries, but you have a lot of development happening in the areas, and you have extra sand. It's just a different approach to soil design, and we wanted to see how this transformed with the soil types. And you can see again the timeline where there's mostly loams, even sort of generally in that loam category. It's kind of an ideal soil, but typical of the area. And then starting to see these more sand added to the soil mixes over time, and to the point where we get into these heavy sandy loams that were more recently created and installed on the sites. And how does that impact the health of the plants and the maintenance of these projects? One item we first noticed was just water usage. Irrigation is significantly different when you have, if you look at again, remember this is the gravelly, loamy sand at African American Museum, and so they have a significant amount more water used there than almost all, than all the museums. But then you see other areas that have a very low water usage, and this is actually the result of some irrigation being turned off after a number of years for failure. And then some sites that require very little irrigation, they actually are turned off in the summer for some areas in those sort of native loam soils. And why does this happen? There's a little bit, we can talk about cation exchange with soils and such, but we'll first talk about the structure of soils. Different soil types have different structures, and we'll talk a little bit about sand, silt, and clay, or clay, silt, and sand, as the screen shows. Clay particles have a sort of the sizes have a flat quality to their particle sizes, which actually lock better together and hold a structure together. So those soils actually resist stress from above. Again, as Marisa talked about initially, there's a lot of people using these sites. So compaction is a big issue. It's always brought up with how you get plants to survive. Compaction, is that a problem? Is it not a problem? And clay soils, they resist compaction quite well, oddly. And it's because the compaction of those platy structures actually distribute that load only into the surface and not deeper down. As you get into silt soils, that compaction will go further, deeper into the profile due to the structure of those particles. And then sand actually has no structure. The actual particles themselves, as larger sand particles, rely on each other to provide that strength to prevent that deeper, create that open void space in the soil. So like when you go to the beach and you pour water through sand, water moves quickly through that because it's moving through those void spaces between those larger particles. Clay soils also have, are able to sort of hide these pockets of air and for water and air to move through, also roots to move through, because there's that structure kind of creates these pockets within that soil. So there's also smaller particle sizes, which have a higher ability to hold nutrients and water and such. But structure is something that's really important to having more resilient soils. We looked at compaction throughout the all the different areas and noticed some areas with heavy compaction just below the surface, some of them right on the surface as well, and some of them were very loosely compacted on the surface, but then there's a deeper compaction just beneath. So we were sort of looking at this throughout. And we also took in a lot of samples, a complete sampling of all the sites. In general, we tried to get sampling for lawn areas and bed areas in each museum, but as we saw different development patterns in certain museums, we took different samples and additional samples for different garden types, so that we had sort of the biggest range. We also did sampling, twice as many samples just to look at all the different soils on site as well, sort of just a visual assessment, so we understood what was on site and which ones we should test. We also did some additional testing for mycorrhizal colonization and fungal spore counts, which we will get into some of those results with Ted Hartzik, who has read all of these and has lots of interesting observations. So I'll pass it off to Ted.
Yeah, thank you, Paul. Yeah, it's interesting. As Paul indicated, we did a lot of soil sampling across all of the museums, and we found some very interesting information, but probably one of the most significant dynamics is there's a lot of variability in the soils around the varying museums. And a lot of that, in a sense, can be attributed to the age of the soils, how recent they've been amended, how they've been built, and how they are managed overall. One of the things that we've been looking at primarily is how much organic matter is in the soil, because we all know, everybody here knows how important organic matter is to soil structure, permeability, drainage, but also nutrient holding capacity and being able to provide nutrients, and then the soil biology. We had a couple of interesting locations. For instance, on the lawn at the Freer Museum, we found as much as 20% organic matter. And typically when you see that much organic matter, as a soil scientist, I look at that as somewhat alarming, because that is a lot, and it creates a very spongy condition that may hold a lot of water. I was not able to see the soil firsthand, but Paul had indicated that really the soil looked like it was in pretty good condition. But that is something we have to look at in the sense that there's too much organic matter. Likewise, what we've seen is, in many cases, especially in the older lawns or older parts of the soil properties, typically the organic matter content can be much lower. And what we see in nature is that every region, every type of soil, the organic matter content is basically, it goes to where nature wants it to be. It's a reflection of the plant growth above it. Obviously, the deposition of organic materials that degrade into the soil, but even more so is the degree of microbial activity that helps to build that soil. And so we really see organic matter content varied really quite a bit across the properties. And with organic matter content, you'll see the cation exchange capacity, which is a great indicator of the nutrient holding capacity of the soil, will pretty much vary along with the soils. The lower the organic matter content, typically we see lower cation exchange, and and accordingly lower nutrient supply capacity of the soil. Next slide. As we continue to look at the organic matter content, as we indicated, for instance, the lawn at the Freer had 20% organic matter content, but we also see, as we indicated, that some of the older lawns, and when I say older, maybe 30 years old, they have very low organic matter content and accordingly really low cation exchange capacity. When you have cation exchange capacity less than 10 milliequivalents per 100 grams, that's pretty low. It's indicative of a sandy, silty type soil, which goes back to the reflection that Paul indicated, how soils started changing at the properties through time. When you have the low cation exchange capacity, you have to manage those soils more intensely. The lawn soils, they'll need more fertilizer. They'll need more organic matter just to be able to sustain the vegetation. Next slide. As we kept moving forward, then we look in the soil sampling, we looked at the overall nutrient condition of the soils. And here we saw a lot of variability. You really could not peg any type of trend. You could not sit there and say, well, yeah, all of your soils have so much phosphorus or nitrogen, potassium, or whatever they may be. It was pretty much all over the board. But at that, really nothing jumped out as alarming. Everything was generally in pretty good condition. What we did see is, for instance, in the beds, in some cases with higher organic matter content, we see higher phosphorus. That may be a reflection of increased fertilizer content. But then again, also at the freer, where we had that really high organic matter content, we had a higher level of salts, a lot of potassium, a lot of sodium. And while these are not extraordinarily high amounts, it may reflect that organic matter that has been added to the freer could be a result of the type of compost that was added. If it was animal manure-based compost, those tend to be high in salts. And that is something that has to be looked at pretty critically as we look at soil fertility and the amendments that we put in. Next slide. We really looked at the soil biology. The soil biology, especially in recent years, is getting a lot more attention than it has in the past. So we were looking at primarily the soil mycorrhizal associations, seeing if we saw any type of consistency with the biology that is formed in the soils. And when we look at that, you look at endomycorrhizal, ectomycorrhizae, we might look at saprophytes for what might be breaking this down. And we utilize the services of a soil mycologist, Efren Cazares, he's out of Oregon, to provide some insight as to what we found. Next slide, Paul. We found some interesting dynamics. Again, nothing was really consistent. Actually, some of the areas defied what we might think we would see in the soil microbiology, but also we saw some trends that provided some good answers as to what might be happening in that subsurface condition that affects how the plants will grow. And as indicated, we were primarily looking at mycorrhizal associations. Soil bacteria also has a big effect on how plants will grow too. But one thing that we want to note real quick is, for instance, in the rose garden at the Museum of Industry, we saw that where the rose garden, similar situations, same type of plantings, where you had the rose garden in the sun, we had a lot of really good root length, very good mycorrhizal associations. We saw really good colonization supporting those plants in there. And it's well known that mycorrhizal associations are very, very important for plant health, plant growth, and sustainability. But in the very same gardens where they were in dominantly shade, the mycorrhizal associations were really substantially less. And in fact, we didn't detect any mycorrhizal associations. Root length was not near as good. It shows that the roots are not growing. And I did some research following this, that basically with the lack of sun, the subterranean environment does not develop as robustly as it does when you have a good sunny environment. Excuse me. The other part of this that we did not show on the slide, though, is that the organic matter content in the rose garden in the sun actually is less than the organic matter content in the area with shade. That's because the microbial activity is so robust where you have sunny conditions, you have a lot of photosynthetic exudates, primarily as sugars, polysaccharides going into the soil. The microbes get going, and what they do is they start using up that organic matter. It burns it off. Whereas in the shade, you don't have that microbial activity, and it tends to accumulate. So there are pluses and minuses in both cases. but the microbial activity is really where we want to be. Other areas, we saw a lot of excellent mycorrhizal associations. And as we move forward, we can describe some or why these were occurring. So Paul, next slide. We also looked at spore counts and fungal spores, because that tells us a lot about that soil environment and the vegetation above. Typically, if you see a lot of spores, the vegetation may be either going into stress, for instance, in drought times, or let's say if there's a physical stress, oftentimes if there's a biological stress. And so the mycorrhizae, in effect, will then start producing spores as their own means of trying to sustain themselves too, so that they could withstand it, produce more mycorrhizal and or other type of fungal associations. So Paul, if you could go to the next slide, we could see how really, as we looked at the counts on mycorrhizal spores, we see that with the associations, for instance, going back to the rose garden, the spore counts really tied up pretty well with the colonization. But we also saw in some lawn areas, and typically you don't see a lot of biology in lawns. But for instance, with the Hirschhorn, the fungal colonization was really good. The spore counts were extraordinarily high. And in fact, if you wanted to harvest that soil, it would be a great inoculant for soil mycorrhizal associations. But the reason we're seeing that though too, is because the trees are in stress. It's a very sandy soil. And so there's nothing supporting those trees. So what happens is those trees are sending the signals down to the mycorrhiza that is supporting them as they go out searching for nutrients and water and everything they can scavenge in an otherwise poor soil to try and keep those trees going and staying as healthy as they possibly can. In a magnolia in the very same area, magnolia was doing pretty well. The lawn was pretty good. Not a lot of root growth. The mycorrhizal associations were very good. And we also saw a lot of spore count. So really what we see is that biology, that soil biology fluctuates with the soil condition and then the plants trying to survive in those varying soil conditions. To the next. What's interesting, what we found from that magnolia, and this is something our mycologist found, and when he looked at he looked at under the microscope, he took all these pictures, is that the magnolia may actually inoculate its own soil environment by sloughing off root cells that have been infected with endomycorrhizal fungi. And so by doing that, it spreads that endomycorrhizae. So instead of them producing spores, they may actually just see sloughed biological matter, the sloughed root cortex that has been infected with this endomycorrhizal going out into the soil, then that can then germinate and move into other roots. So it's a very interesting dynamic. This is something we had not seen before. And in fact, Efren Cazares, who he's one of the leading mycologists in the country, this was something somewhat new to him too. So he's going to look into this a little bit more. So Paul, the next slide. In short, where we're coming from, and what we do know too is soil mycorrhizae, and for that matter also the soil bacteria, which is also very important. They are very species specific, especially endomycorrhizae. For instance, we may have a birch tree, black birches in this case in the planter. You see it's 60% ectomycorrhizal. This is ectomycorrhizae, and most trees are ectomycorrhizae. I get my endo and my ecto messed up. Endomycorrhizae typically are on more native plants, forbs, and grasses. Regardless, the ectomycorrhizae do tend to be very species specific, and in this case, we found that the birch tree tended to be, well colonized with a lot of ectomycorrhizae that are supporting that tree. The spore counts, however, were not very high, indicating that that tree is probably not in stress. The soil conditions are probably pretty good. It doesn't need to go into spore production. On the other side of the coin, we see that in a native perennial bed, there's a lot of endomycorrhizae. There are other trees in that native bed that support the endomycorrhizae, but there's also a lot of arbuscular mycorrhizal fungal spores, which are more of the endo. I keep getting again the endo and the ecto. The endo or the ecto had a lot of spores, but then the endomycorrhizae, if I could get it right, pardon my mix-ups, they're producing a lot of spores. And so they were producing a lot of spores for the other plants that are in these native perennial gardens. So what we're seeing here is this flux, this development of a very diverse, sometimes if you were to look at this in a colloquial term, could be a very violent subterranean environment where all these species are competing with each other for available sugars, proteins, nutrients, and then they're also supporting varying plants. Next slide, Paul. So with that, we used all that information to develop kind of a scorecard or description. Paul, why don't you take it from here?
Well, we took all the different test data, and then we made essentially baseball cards or soil cards, landscape cards, if you will. Anyway, we're looking at these for each site, so that all the horticulturalists can always look at the soils and know, all right, as of 2020, this is exactly the test data we had, and when they test these soils in the future, they'll have this as a reference. So this is a good way for us to track each site. We also diagram sort of what each of those soils look like at each site. So the different types of soil, so whether it's over structure, if it's on a rooftop, the type of soil it is, and then the sample, the test. We know this is actually the exact same soil media used in both of these, so so similar testing would be required. But then other areas that were whether it's lawn over structure, and then what the results of those were versus a tree planter along the median, and how there'd be an existing subgrade layer that'd be compacted, then a thinner layer of this additional sandy loam soil that was added to that. So just sort of keeping track of all the soils at each different site for reference for the future. And as a summary of all this, we found, as we pointed out, soil variability. There's a lot of different soil types here. There are soil trends of moving towards these more manufactured sand-based soils. We did see the soil structure, had some compaction, a lot of compaction at the surface, and then just due to regular usage in this condition. Irrigation use, we noticed that where these sandy soils were, you saw a lot more irrigation usage, particularly in some of that are more recent ones had a lot of irrigation usage. Plant health generally good, with pockets of concerns. We did note some concerns in those manufactured sand-based systems with plant decline in those areas where they were stressed, where the soils were essentially drying out after about 30 minutes on a sunny day. So you have to constantly irrigate those soils for them to really, for the roots not to dry out in some conditions. And soil chemistry, generally nothing of major concern there, but a significant amount of variability, knowing these soils are coming from all different areas and different time periods as well. So how do we create a management plan for all these observations? We started with what are our problems and how do we assess those? Number two is how do we remediate those problems? And number three, the maintenance of existing soils. How do we take care of what's out there? And then the restoration of damaged soils. How do you fix it? And then finally, the preservation of future soils. How do you really take good care of your sensitive soils on site for the future? So the first part is we looked at soil issues at the various areas where there's compaction. We noticed a lot of compaction, typically along in the median, along those along the street edges. Any of those street planters really had a lot of compaction. There's parade routes. There's a lot of people walking over those areas. So that's pretty common. We also noticed some poor drainage in areas. Limited soil volume was also another note where you see sort of swelling root flares and roots just kind of popping sidewalks and such in areas where they just are so compacted they have no real room to grow. So this is an example. We did one of these for each of the sites. And then for new projects, what we found was really the best soil was still the imported soils. These are imported fill soils from the region. Fortunately, the Piedmont region, just over the past the coastal plain, past 95, really sort of north and west of 95, where those Piedmont soils are, offer a really great range of sandy clay loam, even sandy loams and clay loams that are really a perfect soil, and they hold moisture really well. They're more stable over time. They hold nutrients in water. They have, they've led to lower maintenance and irrigation and just healthier plants over time. So we noticed that those sand soils, while they had a lot of organic matter in them at first, that organic matter decomposes. And we saw major declines in a lot of trees after, say, 30 years in those sand-based mixes, with that compost basically evaporating out of those soils and leaving just sand behind. But we noticed that the soils that had been there for 100+ years with these fill soils really were still, great soils for growing large trees. And the plants were still healthy. So we also looked at, how to amend the soils, how to remediate the existing soils. So we looked at two categories, where there were no tree roots and where there were tree roots. So where there are no tree roots is sort of it's kind of the least, the easiest, from just adding a soil surface amendment to something that, actually tilling in organic matter into those soils, or converting turf areas into planting bed areas where it's not necessary to have turf in those zones. And then going into deeper with profile rebuilding, even the deeper depths where you're really picking up soils and sort of decompacting it to a much deeper depth to allow roots to get into those soils. And for areas with roots, again, the same, surface amendments provide a significant benefits to trees versus just basically mulch and compost, which we'll look at in a bit. And then, whether you're looking at soil surface remediation of those soils, really actually getting compressed air to loosen those soils just at the surface level, or doing radial trenching and different strategies. So we took these different approaches, and then we also made a phasing plan for which ones are the most important. So we broke it down into short-term and long-term. The short-term ones are the ones that have immediate needs, and this is something that you should, that we recommend to tackle as soon as possible. So as soon as funding is available, these are areas where trees are showing stress, or you have sort of the best opportunities for sort of grant funding and such. So, and then long-term ones are ones that, the trees are doing okay right now. It's not necessary, but it'd be really nice if you had a project that you could sort of tie those into that project from a remediation standpoint. So again, we offered these suggestions of what were the different benefits. Again, this is a great Gary Watson study looking at tree roots over time under different soil medium, over different soil amendments. And turf, you see very little root growth underneath turf in new trees. And that's because those roots will really compete for nutrients. Grass really takes up that moisture and holds it. And the soils have, they're really competing. Grass and trees always in competition, particularly in the early and later years in life. Whereas under mulch, that's really creating a perfect environment for nitrogen production and tree roots to thrive. So again, this is just looking at, if you can't have fallen leaves, how do you get more of that nitrogen into the soil that naturally occurs in the forest? And so that's if you could sort of do fresh chipping in the summertime from arborist mulch, that actually is a great benefit versus say just chips without leaves. So thinking about these as sort of low cost strategies, or looking at higher cost ones where you're tilling soil at different depths. So going from a 6-inch zone with no roots to looking at how you remediate these soils with where there are existing roots in those soils, looking at loosening with compressed air tools such as air spades, and then working in compost into that soil to sort of decompact that surface compaction to really have those feeder roots really thrive without damaging the larger roots in that surface. And then open radial trenching, a pretty standard procedure, but a great way to reinvigorate older trees. So looking at them in an open field situation, or looking at them in how do you do that in a tight planter along a streetscape. So looking at these different strategies based on current ISA standards for these conditions. And then again, for each museum, we also broke it down into greater depth. So this is the short-term strategies where we really call out where you need to have deep, the pink areas are where you really need to have a deep profile rebuilding. Those soils are heavily compacted where you really want to loosen those soils to 24 to 30 inches as available. And then also looking at sort of areas where you get up to only 12 inches, where you can get a rotary tiller, something that's a little bit, you get a deeper tilling than just a sort of a standard tine-based tiller. So which is more of that surface area amending. And then where you don't need lawn areas, where you can convert those to planting, that is a benefit. If there's not any function to them, you're not having major events or people sitting on them, how can you create more bed areas? And then also long-term strategies where, the trees are looking pretty good right now, but again, in future, how do you plan for that? All right, and so with these plans, again, there's one for each different garden. We also looked at management plans. We created a new, a complete soil planting soil specification that also updating all the soil site protection specifications. So there's clear specifications for all contractors coming on site. So where we've made updates to their existing specifications. And then also thinking about how do you protect roots for contractors? How do you make a quick handout that you can convey to a contractor or someone coming in where roots occur? How do you assess where roots are? So in a traditional environment, you have the critical root zone in an open field where the roots grow out in a perfect circle. And as many of you know, working in urban areas, there are no perfect circles for roots. There are building foundations, there are wall foundations, there's streets where roots do get under occasionally, but under curbs it can be more complicated. So how do you map curbs where you calculate root zones? So you actually take you get the caliper, you determine what the actual root zone is, and then you have that area, and then you apply that in a more of a creative way to map where roots are likely to occur. You have your structural roots, which are shown in this orange zone, which you do never want to impact. You don't want to have any utilities going through those. That compromises the structure of the tree for creating a fall hazard and also a high mortality rate hazard. But there's a certain percentage of areas that you can cut into roots and feel some level of confidence that that tree will survive. So how do you sort of map that? Keith Pitchford has done a lot of work in the area on this type of system, great arborist, and thinking about what are the impacts to critical root zones. So, if you impact about 30%, you have good to great survivability of those trees. Versus if you're impacting over 50%, you should be removing that tree. Again, also looking at the existing tree health. If the tree is excellent, good, fair, poor, or dying or dead, those impact how you make those considerations. If you have a tree that's in very poor shape, impacting it 30% might be too much. Then also the season of impacts. This is a big one. When trees are dormant, it's the best time to hit roots if you need to hit roots from an impact standpoint. But the worst time is the spring. Basically all the energy has come out of the roots and it's up into the new leaves, and the tree is just starting to photosynthesize. And you never want to hit a tree in the spring, even though that's often when someone says, "Oh, we got to take that limb off. You got to do some work." In spring, everyone wants to do some work. So keep that in mind when you're planning around preservation of trees. And then the tolerance to impact. Every species has a different tolerance. These are current ISA standards for which species, and this obviously we're looking in the region for different species which have higher tolerance versus those with low tolerance. So knowing that you have a high sensitivity to impacting roots of a tulip poplar, they're very fragile, brittle roots. So that would really impact that tree significantly versus say a white oak, which is much more tolerant of construction impacts. We also updated all of the protection details. So these are standard details now that each consultant will put onto their drawing sets for how to do protection fencing, really making sure it's chain link fencing, not just that cheap, flimsy orange fencing that everyone takes down, and make sure there's signage on those that's really clear that you're protecting critical root zones. We also, and there's lots of other examples of these. There's also a whole series of specs on how to amend soils, how to place soils when you're doing these new soils on the sites. How do you work with loam-based systems versus people who are used to, say, maybe it might be a sand-based or a mixed system. So there's a whole new set of details for contractors to utilize and consultants to utilize to put onto their drawings. And with that, of course, there's an associated planting specification that is intensive. There's a lot of information. We kept trying to make this as short as possible, right, Ted? And it kept getting longer. But we wanted to give options for people, and they could edit these themselves, and sort of where areas are long lead items. We want to really call out the critical, getting product data 12 weeks ahead of time before you start soil work, and really highlighting what's most important on these specifications for consultants to understand and then convey to the contractor. So there's a whole new set of specifications. And then we also have pre-approved soil suppliers and compost suppliers and people that we like in the region that we've gone and looked at their sources and think they have a good product that we would likely get something that matches these recommendations. It's always important too to look at your base soil when you're working with loam-based soils. You want to actually visit the site where those soils are coming from. These are often, some people may say, we've gotten questions about are we just stripping down forests or farmland and we're just taking all their perfect topsoil? And unfortunately, fortunately, no, but unfortunately, this soil is all a byproduct of the development of industry. Really, we continue to grow in the Beltway, outside the Beltway, and there's lots of soil available through new developments. And so, often these are stripped as they're leveling sites, especially in these Piedmont soils. They're never really level like the coastal plain might be. There are hills, and those are often level for parking lots and such, and other things. So there's plenty of soil available, of high quality soil. And when you see roots in it, or those are actually good things. We don't screen them. We don't take them out of the soils. There's a whole nother discussion on how to protect your soils as you're moving them, but they're all provided in a set of specifications. And you want to look at these soils first. So you kind of put them in. That's a requirement for the consultant to go look at those. Then, what is that perfect soil? What are the ranges that are acceptable that fit into this narrative? And this works for this region. This wouldn't work for if we were in Boston or if we were in Texas, but this is what is really catered to the Smithsonian Gardens and these specific sites based on what's in the area. And then we also have a checklist for the Smithsonian staff to kind of follow along, so they know everything they're supposed to be receiving in these specifications, and these can be passed on to the subconsultant as well. So when they receive data, they know what is the approved range, has it been received yet, when was it approved, any notes you want to add. So you're just tracking all the submittals in the specification. This is just specs are a lot of work. So how do you simplify this for the layperson, just to kind of grab it and say, all right, this is what I'm anticipating, and how do you respond to that? And that about does it. A lot of information. I'm sure you have a lot of questions. I see the chat has lit up, so we're going to start digging into those. Again, thank you to the Smithsonian Collections Care Initiative for sponsoring this work, and we look forward to hearing from you.
Wow, thank you, Paul and Ted. That was really fascinating. I always said that I got into gardening because I really appreciate and enjoy working with soils, and that made me appreciate soils even more for why we should be concerned with what is surrounding or what is in our gardens. There is one question that I thought that came up, and Ted, if you can just elaborate a little bit on what you are talking about for what causes compactation. And you said that you'd be able to discuss it just briefly to be able to share a bit of information with us. Can you tell us more about causes of compactation or compaction?
Yes.
Yeah.
Cindy, what I found in response to that question too, at many of the sites we have, obviously when you have a lot of organic matter, especially living organic organisms too, including the root structure, you actually have a sponge type system that is like a spring. If a compaction force comes down, the organic matter pushes it back up. I have a site in Austin, Texas, where we have that even when the soil is saturated, you could step on it and then just watch it come back up. So the organic matter is very, very critical and important in that. But what we found, for instance, when I did the arch in St. Louis, I was terrified shortly after the site was done. They were going to have their 4th of July on the lawn. And we went, and what I saw was that 2 days after, everything looked pretty good. About a week after, the turf was not looking very good at all. It was stressed, and it was those shear stresses across the soil that were breaking the stems of the grasses, that was breaking the roots. But we had a lot of really good, healthy root production in organic matter. So when I took my cone penetrometer, I found that the soil, even though there were tens of thousands of people across that lawn within a 24-hour period, there was very little compaction. So with that healthy biology, the turf actually was able to recover with some rest. And whereas the National Park Service many times had said, we just in whole replace the grass, they said they didn't have to do it. So there's that soil biology coming into the factor. But the also part is that the shear stress of people walking across a soil, think about it, it's not just a downward force, but it is a lateral force. And that lateral force starts breaking down the soil structure. It's like a mortar and pestle. And as you do that, that causes those particles then to move closer together. And that seems to be, I can't say in a scientifically based condition, but this is what I've seen at many, many sites that is really starting to create that compactive layer. So compaction is not necessarily this, it's oftentimes more of that shear stress that goes across the soil that really breaks it down.
That makes sense. That makes sense. Okay, another one. How do you determine what type of soil in the soil triangle is a good fit for your area? You circled our area. So how do you determine for others?
I could take a quick pass at it. Well, first, knowing what your typical soils are in your area is most critical. You know, if you know you have a general range, so you could do a soil test of you could do a few soil tests in a certain area to say, all right, these are the typical soils. So getting your soils tested, existing soils is really critical, but also knowing that there are certain soils that are better. Say if you're in New York City and you know that you're maybe getting soils from Long Island might have a heavy amount of silt and sand in them. And those are actually they have higher ability to compact. So they may be a poor choice for an urban site. Whereas if you're getting your soils from New Jersey, you may have a higher percentage of clay in there. And again, that gets into that soil structure where you're getting a better soil, where essentially the roads of New Jersey start to get a little wiggly on the map. You may say, all right, that's where I'm getting a little more clay in my soil, and that will actually resist compaction more and hold nutrients better. So getting soils with a little more clay content in there is beneficial in certain areas. But then obviously when you go to Pacific Northwest or Texas or other areas, it's a different model. But and generally in this sort of mid-Atlantic area, looking for soils a little more clay versus in that coastal plain soil types is more resilient from an urban or sort of well-visited site.
From what I remember from school, don't they produce maps in regions so that you can see, they're testing soils all the time, so you could see what is native or what is more common in your area? Where do we find those maps?
There's apps for it now. There's soil maps apps where you can just click in your location and it'll tell you where your what your soil type is in your area. So
I was going to say, as a soil scientist, I absolutely have that on my phone. From the National Resource Conservation Service, you can get the soil survey app. And as Paul just indicated, it'll know where you are, and you click on the button, it'll tell you what kind of soil you're standing on.
I can't tell you the time I spent trying to get those maps from the different areas. So that's great. I'm going to get that app on my phone. That's terrific. When you're using tilling to remediate soil compaction, how do you prevent the smearing of clay particles creating hard pan? That's a really good question.
I'm going to jump into that one, Paul, if you don't mind. Mm-hmm. That is a great question because frankly, and Paul and I had a lot of discussions about this. I hate rototilling for that very reason that was brought up, especially as the tillers come down at the bottom of their sweep, they do tend to create a plow pan, and that's going to mess up drainage. So ideally, on many project sites, if indeed you have to rototill, and many times you do have to, you have to be careful. And oftentimes I tell them to rock the system so that it'll do this. The other part, and this is something Paul provided some instruction on, there are different types of implements that you could use. I always like using just an agricultural disc because in that case, it's not creating that pan, although over time that will. And then also, Paul, you had indicated at one time there's this a rotating type shovel, so it acts like a real spade.
Yeah, the rotary plows, it's making a plow, so it actually is breaking up. You get about 12-inch depth with those, and they're a walk behind that do a much better job. They don't really compact like tillers do, and they get you about 12-inch decompaction. So again, a rotary plow, you can sort of Google those to see what they
That's
look
what
like.
that was called, yeah.
They're pretty,
Okay.
they're pretty terrific.
Well, that's really good. And I have said the same thing with working with gardens. Tillers make the beds look really nice and make it really easy to plant for a while, but it really does cause damage in the long run. So thank you for emphasizing that.
And if I could add, Cindy, I tend to always add, not only do they create the plow pan, but they do tend to shear good stable aggregates. Again, breaking down the structure that Paul had indicated is so critical in good soil.
Mm-hmm.
Yeah, and again, where that rotary plow is nice is that it doesn't break up that structure as much. You still get those clumps and peds in your soil, so a benefit there.
Clumps and peds, I haven't heard that in a long time. It's great to hear it again. Can you remind people, that is there a name of this app, or do we just Google Soil Map app? And because they're interested in putting that on their phone as well.
Ted and I are both looking at our phones now to figure out what it's called.
Yeah, if I had, let me see if I could get it to my camera. No, you can't see it on there.
No, that's right. We'll put it on our website.
If you go to the,
Yeah, it's called
NRCS
Soil Web, but that's, oh, and then we
Exactly.
go. Springhouse, thank you very much for posting that. Web Soil Survey or Soil
Yeah.
Web too.
So
You go
Zach
the,
got it. Thank you,
Soils
Zach.
homepage at the USDA NRCS.
Excellent, excellent. So we have some answers for you on the chat box. Can you tell us how much organic material content is too much? What should we be aiming for in our gardens?
Again, Paul, you can answer, but I'll take a real quick first stab. Typically in soils, if you have more than 15% organic matter content as analyzed, that's considered a histic or basically an organic soil. And at that point, that organic matter can start either holding more water than you want, but also can harbor a lot of pathogenic type microbes. It could also become hydrophobic, so it won't allow water to come in. So it's not always the case, but generally that case, then Paul, you wrote up some good guidelines for the manual that we have.
Yeah, I mean, at 2 to 6% or so, that seems like a pretty healthy range. If you start going above that, you'll see high actual subsidence and evaporation in those soils, like compost, and so those soils will dry out a little bit if it's too much compost. And so anyway, yeah, I think that 2 to 6% is a pretty good range.
4 to 5 is actually a really nice sweet spot.
Okay,
Yep.
we'll remember that when we're doing our testing. And so now there's so many more questions. I'm trying to jump and find out which ones will help out the most. But there was one on, nope, lost that one. Okay, I'm gonna go to the question I've been dying for. Okay, so this is really great work, and I'm really appreciative that Smithsonian Gardens did it, and we're gonna make the reports available at some point to our public gardens in the area. But I'm just a plain gardener at home. You can see how much I garden. No, but what are the most important things I can do for my own garden to improve the soil health, or just leave it alone?
Depends on what's growing on it now. If you just have lawn on there, and you want to convert it to beds, that's a different sort of, you want to sort of reinvigorate those soils. And
let's go with that as a new gardener. That's important.
With that. But for tree growth, again, mulch. If you're putting a new tree in, make sure you're putting down mulch. It's such a basic need to suppress both competition from grass, but also holds moisture in the soil. Sort of replicates more of a wooded situation with fallen leaves and such, really holding in moisture in soil. So those are just real basic, everyone knows them, strategies that I can't harp enough, because I see so often just a tiny little 3-foot mulch ring around a new tree, and then mowers and everything else. But anyway.
The other
Great.
thing I was going to add to that, Cindy, is as we were talking about a few minutes ago, do not over-till your ground, because not only are you breaking soil structure, you're killing off your soil biology, and the soil biology is the underlying factor of soil health.
We have 1 minute left, but I did see one other thing about difficulty importing soil in the DC area. And again, there are some soil providers that you can find out there that are doing this. They're really just a broker for different developers. And happy to sort of point you in the right direction. If you have any questions afterwards, you can reach out to me.
Just email me and I'll be glad to share the emails with Paul and Ted. And it's 1 o'clock and I thank you very much. Our plants appreciate your help. Our gardens appreciate your help. And we're looking forward to see what happens in the future. And thanks for everything that you do. And Marisa, thanks for you. We'll see you next week. Bye-bye.
All right.
Thank you
Thanks,
very
everyone.
much, everyone.